Right, we're now in chapter 2. We're going to be talking about polynomials and rational functions. First thing we'll start with are quadratic functions, so your parabolas. And I'm starting off with the standard form. We talked about this back in 1.4 already, so this should be kind of a review. So when you see the standard form, you've got a number out front that's going to impact your opening pattern. If that's positive, you're opening up. If it's negative, you're opening down. And the number in here with x is going to impact how far left or right your vertex is moving, always opposite of the sign that's in there with it. And whatever's at the end, that's how far up or down your vertex is going to move to begin the graph. And there just states that down below. And the opening pattern, I'm going to fill this in. If you haven't completed the tons of tiles challenge problem at the beginning, stop now and run through that so that this part makes sense. That's going to help you understand why this opening pattern happens the way it does. So for a typical parabola, let's just say y equals x squared. Okay, well, some points on that parabola. Well, we have 0, 0, we have 1, 1, 2, 4, 3, 6, no. We have 3, 9, we have 4, 16, and we could list plenty more. So at the vertex, start at 0, 0. The first time you go over 1, so as I go 1 to the right, I'm going up to 1 for y. Now if I go one more over, so let's put that on the graph. If I go one more over, now I jump up to 4. So I was at 1, 1. If I went over 1, I went up 3. And if I jump one more, I go up to 9. That's getting off the chart there. But if I went from 4 to 9, I went up 5. And hopefully you're seeing that pattern unfold. You just run through all of your odd numbers. And what ends up happening, if you have whatever your a value is, you end up multiplying by that to figure out your opening pattern. So if we had y equals 3x squared, all right? So we would go up 3, and then 9, and then 15, and then 21. And we can fill that in real quick if you wanted to, just do a few, just to confirm. So 0, 0 would be on there. 1 would be 3. Put in 2, you get 4 times 3, so 12. 3 squared would be 9 times 3 would be 27. So we go up 3, and then we go up 9, and then we go up 15. So let's graph one just to review it a little bit, make sure we understand the how to put them on a graph, how to do the opening pattern. So start with the vertex. This one's going to be at 3, 5. So we go over 3, up 5. All right. The a value is -2. So this is going to open down. Now normally if I go over 1 either direction, I go up 1. Well, this will be times -2, so I'll go down 2. And normally if I go over 1 more, I go up 3. Well, this will be twice that, and it'll be negative. So I'm going to go down 6 every time I go over 1 more, left or right, and so on. 5 points is typically enough. That's what I'm going to ask you to at least give me 5 points when you do your graph. And one of those points does need to be the vertex. That's really important that the vertex is on there. All right, let's run through that process of completing the square. Typically, we'll get trinomial or parabolas in the form of a trinomial, and it's a little trickier to find your vertex and your opening pattern this way. If we're going to complete the square, the first thing we really need to do is to take care of this number by itself, this constant on the end. You may have seen this kind of pushed to the side, which is fine. It can be done that way. What I've found over the years that seems to work the best for most all students is let's just move it to the other side. I'm just doing some algebra, so if it's -13, I'm going to add 13 to both sides, just get it out of there. So y plus 13 is -2x squared plus 12x. And we really need these two x terms together. It it'll go a lot smoother if they're already just kind of by themselves, so you don't have to do as much you don't have to think about what to isolate, what to push aside, all that stuff. Now, whatever's in front of x squared needs to be factored out. It's nice this time because 2 is going to be a common factor to both terms, but you don't always go by common factor. Whatever's in front of x squared, that's what you're going to factor out. So I'll leave the left side the same, and we'll take negative 2 out. So again, whatever's in front of x squared, you factor that out, no matter how complicated it makes this second part. Sometimes it's going to be a fraction over there that's going to happen, and that's okay. All right, so take negative 2 out of that. Take negative 2 out of 12x, you're going to get minus 6x. And always do a quick confirmation, distribute back out, make sure it all checks out. Now, we can stop there and start a new step, but the idea is I'm going to add something in here to complete a square. And the way we figure out the thing that's going to go there, and I'm going to explain this in just a minute, we're going to prove it. Take whatever your middle term is, in this case negative 6, and I'll do this off to the side. You take that negative 6 and you divide it by 2, which is going to be negative 3. And then once you do that, you square it. And that's going to give you 9. So really the sign isn't even that important. If you just take the number, so 6 divided by 2 is 3, and then you square it. So divide by 2, and then square. Again, we're going to explain that process. We're going to prove it after we get done with this example so you see why it works. And that's going to be a theme of the class. It's important to know how to do the math, but it's even more important to understand how it works so you can understand what you're doing when you get to calculus. You really need to understand really what's going on in the background next year to really understand what's happening. So let's run through it. Y plus 13 is negative 2 times, and I'll just fill out an x squared minus 6x plus 9. Okay. Now, this part in the parentheses, that's a perfect square trinomial. That's going to be x minus 3 squared. You do a little bit of factoring to confirm that, but the shortcut is whatever you got when you divide it by 2 right here, it's going to be x plus that number. So we took negative 6 divided by 2, got negative 3, it's going to be x minus 3. And last thing to do, let's push that 13 back to the other side. So that way we would subtract 13, and there we go. So that's the standard form for that parabola. Now we've gone through that process of completing the square. All right, usually in class at this point, this is kind of the challenge for you to prove it. And I'd give about, 10 to 15 minutes just kind of seeing how it's going. I'd get you all to work in groups, and I'd probably stop you and kind of give you little hints along the way. So what I'm going to ask you to do, and this is really for your own sake, it's going to be worth it if you do it this way. Just, if you're not writing down notes, get some scrap paper and just kind of do this step by step with me. I'm going to give you a little task to do. I'll tell you when to pause and when to check out what I'm doing here. So first thing is to expand x plus n squared. The whole point of this, I'm going to show you why. We're going to prove why completing the square works like it does. Okay? So I'm starting with a perfect square binomial, which is what you get when you factor a perfect square trinomial. So this should work out to a perfect square trinomial. All right, so pause now and expand this out. Once you've done it, check back in with me and see if your work's matching mine. If it's not, see what you need to do to get it right. So I'm just going to use a little shortcut, x squared, then x times n times 2, and then n squared at the end. And that's our expanded form. All right, there it is written out. Now, there's an understood one in front of the x squared, so that's our a term. If we're talking about trinomials, a, b, and c being our coefficients. And I did a little rearranging, put x at the end. So 2n is our b term, and our constant at the end is n squared. So it's kind of a mapping of where all the pieces go when you square x plus n and expand it out. Now the next piece of the challenge, use algebra to change that 2n, that b term, into n squared, which is the c term. So we're going to turn this into that. And hopefully you kind of have a sense of where this is going, because when you complete the square, you're starting off with just two terms. This isn't there yet, and you're going to do something to make that up. And we're doing it in a really specific way so that this term always turns into n squared. So that's where we're going to kind of come up with a recipe for how to make that happen. So I want to be real deliberate here. I'm going to say that 2n is my b value, just to give it something to call it. But I want to solve for n, and I want to turn it into n squared. So pause, take a moment, solve this for n, and then turn it into n squared, and then see what you get. First step to solve it, I'm going to divide by 2. N is going to be b over 2. And if I want to get n squared, I'm going to square both sides. So n squared is b squared over 4. So n squared, and I'm just going to leave it this way, is b over 2 squared. I could expand that and get b squared over 4, but I think that this is actually going to be a little more helpful to explain the process. And hopefully, again, this is kind of coming into view now. We took the middle term, divided it by 2, and then squared it, and that made it produce that last term. It made it be a perfect square trinomial. So that's sort of a mini piece of the proof there. All right, I guess that actually does prove why you do that process. Divide by 2 and then square it. That's the process that you're going to do to complete the square. Because again, you're trying to create that perfect square trinomial so you can factor it back down to a perfect square binomial. The last piece I want you to do is take this trinomial in a trinomial polynomial form. I want you to turn it into the standard form of for a parabola, not hyperbolas yet. And verify your formula with example 2. So we'll go back and we'll ask you we'll run back through example 2, and I'll make sure that what you come up with is going to work. So the way this is going to look, you're not going to end up, I made a little note here, h and k will be defined by a, b, and c. So when you get done, you'll still have a in here. You won't have an h, you'll have some combination of a, b, and c. And for k as well, you'll have some combination of a, b, and c. And it's like giving you a recipe of how you can look at this and know what your h and k are going to be, to know what your coordinates are for your vertex. So pause now, take a moment, complete the square with this, and see what you come up with. As we run through this process, kind of think about what you might notice some similarities to. Some formula that you've worked with a lot that you might really see some kind of common pieces because you're probably onto something. So first step, I'm going to get rid of the constant, or not get rid of it, I'm going to move it over. So y minus c is ax squared plus bx. All right, next up, I'm going to factor out that a. Now, this is one of those cases where there's no common factors, so if you factor, you're kind of dividing out. That's one way to think about it. So if you divided b by a, you get b over a. And if you distribute back out, it checks out. That's going to work. Now to complete the square, let me do this off to the side just so we can kind of confirm it. You're going to take b over a, and you're going to divide it by 2, which is kind of multiplied by half, so it'll be b over 2a. And then you're going to square that term. So that's going to be your third term here. It's going to be b squared over 4a squared. All right? Now, y minus c is going to be a times x, and then it's going to be plus whatever this was when it was divided by 2. So plus b over 2a. And you could always do some factoring. It would probably get pretty tricky here, but it could be done to maybe confirm that. And I'm almost done. I'm just going to add that c to the other side. Go ahead and get that out of my way. So that ought to do it. If you have a trinomial in this form, and if you want to get your x coordinate for your vertex, your h value, that's going to turn out to be b divided by 2a every time. And if you want to get your y coordinate for your vertex, it's just c. So there's your h and k, and let me just kind of make a note of that. H is b over 2a, k is going to be c. Simple as that if you want to find your vertex. And we'll double check back on example 2. Hopefully you're kind of thinking about some elements that are happening here. We're going to lead to another proof coming up really soon. So if you didn't catch on to anything that looked familiar, then Don't worry about it too much. Use that b over 2a, kind of gets people thinking about something familiar. But again, we're going to explain that here in a couple lessons coming up. So I did ask you to check with example 2. Let's see if that's how it unfolds. Let's see if the h value is b over 2a. Let's see if the k value is c. So let me run back. So b divided by negative 2a, that's going to be our h value. So 12 divided by negative 4 would be 3. Now one little catch here, or I'm sorry, it was negative 3. If I flash back real quick, I probably should point this out earlier. It's x plus b over 2a, so it's actually the opposite of that, because our vertex is at x minus whatever this is. So just keep that in mind. If we had, so this should be x minus 3. That's what goes in the parentheses anyway. So positive 3 is actually the vertex value. And c was negative 13 in the beginning, and that is our k value in the end.